walking through Harlem, and she was pregnant at the time. We saw posters that were advertising formula. We saw other posters that were advertising breastfeeding. The genesis of this project really was, I think, a humanist sort of perspective, where we were just trying to figure out, why is there a debate about how we feed a baby?
That question is what spurred Dr. Stephen Townsend's award-winning research on human milk and helped land him on Chemical and Engineering News 2019 Talented 12, a list of brilliant young scientists taking on some of the world's toughest problems with clever chemistry. In this 6-part Science with a Twist series, which we're calling Bringing Chemistry to Life, we'll speak with a selection of the Talented 12 about their work and trend in their fields. I'm your host, Paolo Braiuca, Senior Manager of Global Market Development at Thermo Fisher Scientific. We began by asking Dr. Townsend, Assistant Professor of Chemistry at Vanderbilt University, about his career path, starting out as a first-generation college student in Detroit to working with some of the biggest names in the chemical field.
I am the oldest of 5 kids. I grew up in a single-parent home in Detroit. One thing that's pretty interesting, though, is that I'm actually the oldest person in my generation. So I have no older siblings, no older cousins. So you can imagine the sort of like superiority complex that accompanies being the oldest. So, as a kid, I was an athlete. I'm big time into football and basketball, into track. But I also really love science a great deal as a kid. I always tell the story that when I was in elementary school, my mom was looking for different literature on Black scientists because she wanted to hand me a role model that I could sort of, model my behavior after. She actually had a hard time finding very many books on Black chemists. So for her, she did the next best thing, and she got me a bunch of literature on Louis Pasteur. So I remember, in the 4th grade, writing this essay about how I wanted to be like Louis Pasteur. The teachers thought I plagiarized this thing that my mom wrote it. And my mom came to my defense, like, trust me, I'm not writing any essays on Louis Pasteur. But that was sort of the beginning, right? I was just a kid who loved science. I went to a math and science type of high school in Detroit. Studied chemistry as a grad student, as an undergraduate as well. And then, from the Danishevsky lab, just really got deep into applying chemistry to biology problems.
It's great. So if I look at your early publications from the Danishevsky days, I see a lot of hardcore organic synthesis, mechanistic organic synthesis. How did you transition to this carbohydrate chemistry work that you started doing later?
Carbohydrates have always been there. So, when I was an undergrad, I actually did 3 years worth of nucleoside synthesis. I got away from carbohydrates when I was a grad student because I focused mostly on terpene synthesis. And then within the context of terpene synthesis, we were doing photochemistry. And this was before photochemistry became cool again. So I was taking out the big giant lamps, blinding everybody in the lab, trying to do reactions. But going back to the Danishevsky group, I basically just went in there with open eyes and did any project that he asked me to do. And that was pretty tricky because with Professor Danishevsky, that means that there's going to be somewhere between 3 and 45 different ideas per day. And most of these ideas are going to be good. And you're like, what do you want me to do? And he doesn't know what he wants you to do because he's just constantly generating ideas. So what happens? Ultimately that means that I do some mechanistic chemistry. I did some glycoprotein synthesis and carbohydrate synthesis. And I realized that we didn't have enough carbohydrate synthetic chemists in the country. So that's what I wanted to start out with, at least for part of the group when we started at Vanderbilt.
Synthesizing oligo and polygosaccharides is renowned as being quite challenging chemistry from the synthetic and analytical point of view. Did the years at Danishevsky's group give you some sort of edge, some sort of different perspective to the chemical problems you can encounter there?
Yeah, there's no question. So, if you go back to the old German literature, they usually consider carbohydrates as the second most difficult class of molecules to make. And this is after alkaloids, which is considered the most difficult. And so I think the benefit of being in the Danishevsky lab was that, you have chemists worldwide from China, from India, from Japan, from the States. I met a glycoprotein chemist from Paris. So I think, you're bringing just the world's greatest scientists together, and then you can learn from everyone. And so, as a graduate student, my anhydrous technique was not good. When you're doing total synthesis, right, you're just pounding through and trying to get as much material as possible. But I really learned how to get things dry when I was at the Danishevsky lab because 2 chemists, Ping and Sue, taught me about anhydrous technique and how you can't do carbohydrate chemistry if you can't get things dry. So I think the collection of talent that was just present in the lab, it really sets you up for the future in a way that is pretty unique to that system.
So you seem to be very smart in making the most out of the connections and the the knowledge around you and the people you work with in the lab and also you collaborate with in from different labs. Am I right?
Oh, that's right. In a way, I consider myself a humanist. So when I was an undergrad, I took as many classes in sociology as I did chemistry because I love human beings. I love game theory. I love interacting with other people. And so I think that there's a real power in leveraging connections and leveraging each other's knowledge. I have a specific skill set and I can apply that to a lot of problems, but there's far more things that I can't do. You don't have to do everything. There are people who are experts in fields that you need. If you come together, you can do something powerful.
And it's interesting because probably your most popular line of work is around the human milk oligosaccharides, which is really interdisciplinary, isn't it? We need to start from there, right? And this is what won you considerations for the Talented 12 program. And obviously, there's a lot of fantastic papers that I read. And you seem to be developing a lot of knowledge with some incredible potential there. So, effect on gut microbiome, antimicrobial activities, effects on immune system. There's a lot there. I guess we should start from the idea. Is it really true that you were inspired by some formula advertising?
Oh, yeah, this is totally true. My wife and I, she had just finished graduate school at Columbia. I was finishing up my postdoc. We were walking through Harlem and she was pregnant at the time. We saw posters that were advertising formula. We saw other posters that were advertising breastfeeding. We started to think, one, is there any strategy behind the placement of these posters, right? Are we promoting different ways to feed a human being to different people, maybe based on how they look and how much money they make? And it turns out that in a way we were. The genesis of this project really was, I think, a humanist sort of perspective where we were just trying to figure out why is there a debate about how we feed a baby? It seems like that there's, one gold standard. It should be easy to adopt that across all people, but, not so fast. It's a very controversial topic and it's not that simple.
And so, of the many different lines of detour of that research, going into the gut microbiome or going into antimicrobials or whatever else is coming out for that fantastic work, is it, what do you foresee as being the best or the highest potential future application in real life application?
So the graduate students in lab, they usually make fun of me because I make fun of Professor Danishevsky for having 45 ideas per day. And they tell me if he has 45, you probably have 10 or 15. If we think about what these molecules do at their core, right, because we take them in a lot of directions, but what they really are built for is to feed good bacteria and in a way to kill bad bacteria. So I think that a coming project out of the lab where we're actually using these molecules to prevent colitis in the gut, inflammation of the gut, is going to be a really, I think, a unique application and one that can be applied to people that are not babies. Because we have some really cool data. It should be out within the next 9 to 12 months that demonstrates that we can prevent things like Crohn's disease in a mouse model by feeding mice human milk oligosaccharides.
Do you see future applications of these compounds or mix of these compounds in future drugs?
I do. I think it's going to take a while to get there. So if we look at where we're at now, there's a single compound, 2' fucosyl lactose, 2' FL, and that's being added to a lot of infant food products. So that's good. We want to start getting HMOs into all products for all babies. The problem though is that mother's milk is really personalized for her baby. And so we could get in a scenario where we're feeding babies 2' FL, even though their mom doesn't make it. Right. And so I think that there's a lot of the puzzle that we need to unravel before we can really get excellent use of these compounds, because we really need to know which molecules are most important for what baby, and then how do we get that into a personalized formula for that specific child.
So these days, when there's a lot of speaking around personalized medicine, moms should be the model to go after.
Oh, I think mom absolutely is the model, because if we can personalize formula, right, then there's a chance that we don't destroy breast milk. One of my big fears is that we could possibly harm or destroy breast milk by misusing these compounds. But as you were saying, if we can personalize every formula that we make based on mom's design, then there's a chance that we won't go down that bad pathway.
How much do we understand there? So when we speak about breast milk being sort of personalized to the kid's phase or needs, do you mean that every batch of mom's milk is really different in the composition of HMOs and other components? And how much do we understand of that? How does it work?
Yeah, we understand very little. It might be less than 5 or 10%. And we have known for a long time that over the course of lactation, so from say 0 months to 2 years, we know that the composition changes pretty rapidly. But there's growing evidence, we have it in our own lab through analytical chemistry, mass spectrometry data that shows that over a single lactation, the composition of milk changes. So if baby is nursing for 15 or 20 minutes, the HMOs that are present at the beginning are not the same ones at the end. Why that is and why mom changes the design, we still don't know yet. And I think that's sort of a key link in being able to apply these compounds for human health and wellness.
It's interesting. And there's a lot of biological work there. And yet you're an organic chemist. So I'm fascinated by this. And I went reading your literature and I found an interesting statement in your paper on accounts of chemical research in 2019. Let me read it. It's at the beginning of your abstract. You say something like that. This account describes the risky proposition of organizing a multidisciplinary team to interrogate a challenging problem in chemical biology, which is characterizing how human milk at molecular level protect infants from infectious diseases. There's a lot of interesting concepts in this statement, but I'd like to go to the beginning. The risky proposition of organizing a multidisciplinary team. So chemists and biologists don't really speak the same language today.
Oh, we're not on the same page at all. Biologists, they think small because they're thinking at the micro level. Chemists think smaller. We're at the level of elements. So when we get together, there's a lot of miscommunication. At least when we started our program, there was an inability to formulate a hypothesis that we both understood, that chemists and biologists both knew what we were trying to get after. But those are small barriers because the more you communicate, the easier project goals become defined, the easiest you can develop hypotheses, and you can move forward. But I think anyone who organizes a team in this manner, where you have people from different fields, is absolutely going to be bumpy just because we all think differently. I have colleagues in microbiology who thought that no one could think smaller than they do at an atomic level until they started working with chemists who actually think about splitting atoms.
How did you overcome these challenges? Or do you have a trick to share?
So I'm always a person who likes to, the quote is like, stay in your own lane. My expertise is in synthetic organic chemistry. I make and break bonds. I have who I think is the world's best collaborator and Professor Jen Gaddy, who is an excellent microbiologist, and she's an expert in single electron microscopy. And so when it comes to doing chemistry, whether it's for my projects for her or for hers, she trusts that I can get the job done. And I think similarly, when it comes to doing microbiology, I just trust that she can get the job done. She trains my students in microbiology. I train her students in chemistry, and the students try to teach me a little bit. I'm 37 now, so it doesn't work that well. But I think experts are experts in their field, and that we can all work together ultimately with the goal of learning from each other and trading skill sets. But you just let people who are experts be experts in their field.
But how do you come with the idea of developing the general direction of the research program? Because you said you're a chemist and you're expert in making and breaking bonds, and there are biologists who are experts in their own niche. But here you need to merge different perspectives and potentially objectives into a sort of bigger vision for it. I'm fascinated by that. It sounds like a very challenging thing to do.
Yeah. So, one of my role models was Professor David Jen, the late Professor David Jen. And I think he was excellent at merging very complex organic chemistry with very interesting biology. And so I knew that when I started my independent career, I wanted to do the same. And the way that we were able to do that was by going to a meeting about preventing adverse pregnancy outcomes. So there's a group at Vanderbilt where specific senior investigators hold these meetings where they want to bring people from all fields together under one umbrella. Here I am with a couple of my graduate students at this meeting on pregnancy. We start to learn about group B strep. One thing that really stood out was that babies who drink formula are at an increased risk for developing group B strep, even though formula is sterile. Yet babies that are breastfed are to reduce risk of developing group B strep disease, even though group B strep is present in a lot of mother's milk. So to us, that was a chemical connection in this really interesting biological problem that they were addressing. So that's how we formulated our first team. We saw an interesting chemistry solution to a biological problem that they had, and we all got united to solve the problem.
It sounds like the scientific culture at Vanderbilt is nurturing this kind of approach. Is that true?
Oh, it's mandatory. I interviewed at a couple of places, and Vanderbilt was the only place that I interviewed at where I sat down with the provost of the university, and he said, "This is not a place where we work in isolation. At Vanderbilt, you're expected to solve bigger problems, problems that are bigger than yourself." Provost McCarty at the time, he said, "I would love to see you use chemistry to solve food security. How can you do that?" And I was like, "I don't know how I can do that, but I can do something else in chemistry that's right, that's multidisciplinary."
It seems like the most exciting research is really going on between the interfaces, at the interfaces between different disciplines, isn't it, right? Chemistry and biology is one you work into, but there might be others. And if I think about the perception of chemistry, I think it is somehow these days perceived as a discipline where there's little innovation going on, while biology is booming. There's a lot of different niches in biology where the innovation and progress is massive and very fast. While probably the interface is a more interesting area. What's your opinion on that?
I love the idea of using chemistry to solve challenging problems in other areas. And you can create and develop challenging, thought-provoking chemistry while you're solving thought-provoking biological problems. People like Jen Prescher at UC Irvine, Laura Kiesling at MIT. These are great examples of people who leverage very powerful chemistry to solve really cool problems in other areas. So yeah, I think that, as we move forward, more and more chemists really do need to move to interfaces with other areas because we have awesome tools that other areas don't have, and we can really address some really neat problems.
And thinking about chemistry and biologists and chemistry and biologists together, you still make a lot of your oligos in the lab, in vitro, right? While nature does things in a possibly different way and very often coming out with very complex products that are mixtures of different oligomers. Do you think the chemical methods can still compete with the natural methods of making oligos, or do you see this more of a synergy?
Well, so it has to be a synergy. So if we project forward, right, 25 years from now, my hope is that we aren't still having to synthesize very complex oligosaccharides. There are compounds that we don't want to make synthetically, but we have to because the enzymatic and chemoenzymatic methodologies, they aren't able to produce molecules at the level of complexity that we need. But, absolutely, at some point, I should be able to go to a pool of E. coli or some yeast and have them make the compound for me. And then maybe right, do some last minute manipulations. So we're not there yet. And that's one of the prime reasons that we're still doing a lot of heavyweight synthetic organic chemistry. But we will be there at some point where, hopefully we won't be making these complex molecules in lab.
So the future of this chemistry is synthetic biology and microbial fermentation?
Absolutely, I think so. And so, 2' FL is a good example. That's just a trisaccharide, but no one synthesizes that. That's made through fermentation. Now, if you go a little bit more complex than that molecule, the methodologies just aren't there. And I know because I looked for them yesterday. So there's, 3 compounds that we desperately need for some mechanistic work that we're doing. And, if I want to buy 50 milligrams of any of these compounds, it's going to cost me $8,500. And so we can make the molecules cheaper than that, and we can make more of it, right? So that's where we're at, right? We're the future is going to lie with fermentation and manipulating bacteria, and hopefully it gets here fast, but it's not here yet.
And despite that, despite the future being microbial fermentation, do you think there's a lot to learn or a lot to change for the synthetic approach for these compounds from the way nature does it?
Yeah, nature is extraordinarily selective, more so with proteins than carbohydrates. Carbohydrates aren't genetically guided to a very strict level. But yeah, I think when it comes to synthesis, we can be much more selective. If we can build building blocks, monosaccharide building blocks that have 5 different protecting groups, if we can make those in 5 steps, that's a Nobel Prize type of accomplishment. So yeah, I think if we can start to get glycosylation under control a bit more, if we can take a little bit of the ambiguity and the guessing game out of carbohydrate synthesis and be a little bit, neater, just like nature is, we'll come a long way.
Will we see any more work from you on total synthesis of non-carbohydrates, or you think carbohydrate is going to be your future?
So that's a tricky question because I love all molecules. I love terpenes. If you ask me what's my favorite class of molecules, they're terpenes. But there's just so much to do in carbohydrate chemistry that I feel like we're going to be there for a while. But you will see some non-carbohydrate work from us, but not in the way you may think. So one project that's starting in lab, it was inspired by Gilbert Stork. We talked about it in a hallway when I was a postdoc. But it's this idea of using carbohydrates and the stereochemistry that's embedded in carbohydrates to access non-carbohydrate molecules that are inaccessible from any other reaction. That's one thing that we're trying to do now. We're looking at carbohydrates. We're trying to figure out how can we convert a carbohydrate into a terpene, a carbohydrate to an alkaloid, just really leveraging the stereochemistry that is in sugars in a way that, maybe we've done that in the past, but not at a very powerful level as a community.
And you mentioned a lot of influences for your own development as a scientist, but they were all scientists, I think, at least I have understood. So many scientists I know get inspiration from other fields. And of course, you've been brave in exploring biology, and obviously you're very good at collaborating and communicating with scientists from coming from different backgrounds. But is there any other form of inspiration from you which is not necessarily strictly scientific?
Absolutely. So, one thing about me that many people don't know is that I'm a big fan of psychological thrillers. So I try to, I've upped my pace due to the pandemic. So about every 3 days, I read a different novel. And so again, I love humanists. And so I think other inspiration, people like Malcolm X, Huey Newton. I love people who led in other areas that are not science because everything that they've done is applicable to how we have to do chemistry. I have a lot of friends who are non-scientists, people who are sociologists, anthropologists, a lot of friends in English, a buddy in the math department, where I can find commonality with anyone, whether it's Malcolm X and some stuff that he may have written in the 60s, or is, my friend Greg, who is the security guard at my 2-year-old's daycare. I just try to connect with people, regardless of what their occupation is.
And as we're coming towards the end of our chat, which has been very, very inspiring to me, I'd like to get your view on the current chemical market. Do you find it easy to source starting materials, what you need, with a lot of innovation going on in your field? Like things like reagents or laboratory essentials of the right quality for what you're really doing. Would you see the need for any improvements in the market to facilitate what you do?
To answer your first question, we do see the quality of reagents and compounds that we need. But I think one thing that's tricky, especially for the students, because they're the ones who do all the purchasing, but it's just the disparity in prices. So you have some companies where I can get, a kilo of xylose for $50. But if you go to another company, a kilo of xylose might cost you 2,500. So I think the disparity in costs, it actually limits the amount of suppliers that we can go through. The standards of excellence when it comes to producing good chemicals has really risen in 2020 that there's not too much difference between each company, but the prices are insane, the price differences.
Thank you. That's obviously an extremely important comment and a great feedback that they take home and ensuring that we look at as an organization. Besides pricing, is there anything that you believe suppliers in the market could do better to support your research?
So I teach a graduate course every fall is structures, mechanisms, and reactions. And when I teach students about reactions, I teach them how to run the reaction. And one thing I always tell them, and it's a sad comment to have to make, but is that you don't trust what's on the bottle from the company. So a good example is say N-butyl lithium. You buy that as a solution, and it always lies on the bottle and tells you that it's 1.8 molar or 2.5 molar. And I tell the students, it's sad to say, but you can't trust the company because I titrate these bottles and I get anywhere from zero point 0.6 to 18 molar. So I think there has to be an increase for a lot of companies in quality control so that students can trust that what's on this label is actually what's in the bottle.
Thank you. That's great. And it can have serious implications for safety, particularly when you handle pyrophoric compounds like butyl lithium or things like that.
Oh, absolutely.
Is there one piece of advice you'd pass to a young scientist or a chemist just starting their career?
Yeah, so I have two. Ask for help. So when I started out, I wrote some of the worst proposals ever for grants, some of the worst papers, and it actually shocked me a bit because I'm a person who, the sheer volume of literature that I read, I thought that I had a good handle on writing, whether it was a paper or a grant. Neither was true. So I would say that, you should ask for help because universally in this community, I've seen people just willing to help me. I can't think of an example where I've asked someone to read a grant or a paper before it goes out and they said no. So I think that you have to ask for help. This is a job where we take the idea of being an independent researcher a bit too serious. The second piece of advice is to take care of your health. I'm telling everybody who I possibly can about this. I'm 37. I'm a guy who, I've been able to dunk a basketball since I was 14, and I'm only 5'10". And so I thought I was in phenomenal shape, but I go to the doctor for my 37th birthday checkup, and she tells me that my blood pressure was high, cholesterol high, sugar high, fats are high. And I told her I didn't understand because I feel great. But she says, sure, everyone feels great until, right, something happens. So I've been on a massive health kick during the pandemic, lost, I guess, 30 pounds or so, running a lot more than I used to, just really watching what I eat. And I think people just really should take care of your health. Don't let Google or Yahoo search be your doctor. Go to the actual physician.
That's a great comment, Steve. I mean, we should all take care of our corona belly that we have developed in the last few months, I guess. The final question from me, is there any other thoughts or comments that it would be precious for you or your research team to share?
I think operating at the sort of nexus of multiple fields is really important and cool, and it allows you to solve or attempt to solve some really interesting problems. One thing that you can look forward to from our group in the future is that, the Milk Project has got us to where we are now. The students who drove that project are phenomenal thinkers, and you're going to see them, branch off into their own independent careers pretty shortly. That makes me happy. It also makes me sad because they're going to basically be coming after me and replace what I do. But that's okay. You train your students to become your future competitors and you help them compete against you. It's a cool process that I actually like. But we have the HMO project, but we have other projects that are operating at the interfaces with other fields. One that's really cool is this idea of is it possible to change the way we think about birth control? So this is our next big topic. What we're trying to do is design molecules that are both selective and spermicidal, right? So they can kill sperm, but they're also able to kill specific sexually transmitted infections. So in more crude terms, perhaps we call it a condom and a pill, but is it possible to provide a single medication that can maybe eradicate trichomonas, but also prevent pregnancy? These are sort of the really big things that we're trying to think about in the lab. And it's all because, we're organic chemists who really don't know what we can't do in biology. And then we have biologists who are like, well, yeah, maybe you can do this in biology, but they don't know how to do it on the chemistry side. So we come together and we can address these really sort of innovative problems.
So we need to keep a look out there for some progress in this field. That sounds like another extremely exciting line of research from you guys.
Yeah, I think it's going to be a fun one. If you think worldwide about the number of women who want birth control but can't get access to it, not because of availability, but because maybe it's the law in their country. This can make a really big inroad to that area. And then on the opposite side of the coin, one of my students came in and was like, did you know that 1 million people per day contract a sexually transmitted infection? And I did not know that. That is a lot of people. I think these are two areas, right, that if you can merge them together, you can really come up with something big.
Is this still going to be linked to the oligosaccharide chemistry, or are we speaking about a completely different part?
Yeah, so it is oligosaccharide chemistry. These are not human milk oligosaccharides, but they are what I would call a glycoconjugate, right? So carbohydrate connected to another type of molecule.
So it is true that the carbohydrate chemistry is going to keep you busy for the foreseeable future.
Oh, it's going to pay the bills. And what's cool, again, like I said at the at the beginning of this question, is that the training environment in our lab it's really encouraging people to think about how they can leverage the power of carbohydrate chemistry to solve biological problems. Right, we're going to see a generation of thinkers who are far more powerful than I am, who are just going to do extraordinary work.
That was Dr. Stephen Townsend, Assistant Professor of Chemistry at Vanderbilt University, and one of the Chemical and Engineering News Talented 12. Thanks for joining us for this episode of Bringing Chemistry to Life, a Science with a Twist series. We'll bring you more conversations with the Talented 12 every other week. For new episodes, subscribe wherever you get your podcasts, and you can visit labchemresources.com for more information about Thermo Fisher Scientific's laboratory chemicals. This episode was produced by Matt Ferris, Gabriel Rama, and Emma Jean Weinstein.